Thank you, guys. As you have seen, too much water can be disaster. It's flood. So what about too less water? So today I'm going to tell you a story of drought. So I'm Kai from the University of Alberta, PhD student with Dr. Evan Davis and Dr. Dan. Today I'm going to introduce the Invitational Drought tournament and its dynamic water balance model. Take a look at the outline, context first, and then followed by the Invitational Drought tournament, and the two versions of the IDT model, model application, and the next step for our model. So the frequency and the severity of the extreme weather events, such as drought, which the IDT focus in Canada is rising, and the IPCC has concluded the events will become more frequent over the next 50 years. So let's take a look what happened in Canada. So the drought do affect the environment, the wildfire. They actually burn money there. And also the agriculture, decrease the agricultural yield. The society suffer from drought as well. Then the Agriculture and Agri-Food Canada recognized the potential impacts on the agriculture. They thought the planning and adaptation now will better prepare Canadian agriculture for inevitable future droughts. So they then developed a decision support framework, the IDT, so the Invitational Drought Tournament. In the IDT, they want to use this kind of framework, reduce ecological, economic, and social drought risk over the short and the long term. So basically, they use a gaming format. It's kind of a workshop, but it's a workshop with a winner. There are several multidisciplinary teams. Typically, each team have 5 team players representing the policy, economic, agriculture, industry for the assurance of the successful adaptation. And those teams just compete in this framework for the best score in the IDT. And also a fixtures basin was graded for the game. The current drought condition in this basin and the mitigation budget will also be provided at the beginning of the game. So based on those information, the players just choose some policies, including water, financial, management, and technological improvements to reduce the drought risk, subject to their mitigation budget, which changes yearly. So here is a policy selection sample. Here offers you the water, financial, and land management policy. They also have an investment in research and development policies. It's also the time frame, long-term policy or short-term policy, descriptions, cost as well. Then, to date, the IDT, the 3 runs of the IDT. The first is Calgary, 2011, and then Saskatoon, 2012, and Kelowna. So then, during the game, players want a model because in the real world, the government just make the policy and just implement to the whole society, get some response from the society. Are those policies effective or not? But in the IDT, in the game, the players just choose the policies they want and spend the money. And then what? They also want feedback. And from where? So they just want a simulation model there to actually memory and compare the policy effectiveness between different game turns and between different games, different teams. Then IDT model, actually it's a dynamic simulation model, was graded and being used during the game to show the policy effectiveness to the players. And the methodology for this model is just system dynamics. This method was graded in middle 1950 by a supervisor in the MIT and widely used until now. So basically it used nonlinear feedbacks, stocks and flows, and delays to describe the real-world structure. So here is a very simple example. There is stalks here, represent a reservoir, and there are inflow and outflow that can change the reservoir value, actually the storage, water storage in the reservoir. Another example, just like, for example, we have a heating system in this room. We want to set a comfortable temperature, let's say 20 degrees of this room. Then, if the room is too cold, the heating system is on, and the room temperatures rise. When it's reached 20 degrees, then it's just off. So that means the room of the temperature can affect the heating system, and the heating system can also affect the room temperature. So I affect you, and you affect me. So there is a loop there. Actually, it's feedback there. So that's the key concept for the system dynamics. And we developed and run this model in Wang software. It's quite like Stella. So let's take a look who can use this model. Before the game, the technical people, they just set the basic characteristics in a spreadsheet. For example, they want to input the, let's say, population and annual precipitation to the model. And the model will just read the data from the spreadsheet. So this is very easy to change one basin to another by changing the values in the spreadsheet. And during the game, the player just choose policies for the drought preparedness and in the policy selection page. Finally, the technical people will run the model and give the results to the team player. We now plan to let here's the pictures, here's the basic characteristic, and the players choosing policy, and technical people running the model. But right now, we just plan to let the players to run the model themselves, and they can get the result themselves to see how the policy affect the whole system themselves. So basically, this is model components and a structure. So the players choose the policy here, input to the model, and the model gives them the results. And the players will just think about how to choose the next year's policy based on the results of the model. So this is the main model. We got agricultural water use, municipal water use, water supply simulation, and population simulation. For the agriculture part, we got two kinds of line, reed-fed line and irrigated line, and 5 types of crops, 4 types of livestock there. For the water supply, right now it's really simple. It's just the base flow. If you choose to draw down a reservoir or build an additional dam or reservoir, you got some extra amount of supply in your basin. The municipal, we got 4 types of indoor water use and outdoor water use. Population, we got urban and rural population. So this is the real result from the IDT Saskatoon. You can see 5 teams. They choose different policies here and got totally different basin water use. And what really surprised us is you can see the difference between the team result is so clear. You can simply tell the difference between those teams' results. And this is permitted municipal water use. We can see all the teams choose to ration the water of the municipal water. And when you ration the water for the municipal purpose, the model will automatically choose to ration the outdoor water use first, and then ration the indoor water. So the outdoor water has the lowest water allocation priority in the model. This is the gross irrigation diversion. So the lines below this reference line means the teams choose to ration the agricultural water use. And those teams above this reference line means they draw down their reservoir and get some extra amount of water for the agricultural irrigation purpose. Since it takes some time for the players to learn how to use this model, we just wanted to develop the new version of this model to let the players run the model themselves. Then we developed the new version of this model in Wang with the feature of the professional user-friendly interface and drag and drop environment, enhanced graph with dynamic zoom in and out. And this model is developed for the IDT Okanagan from November 2012 to present, and it's still under developing right now. So in this new version, we just add the industry part, 3 types of mines, thermal and hydropower generation plants there, recreation. There is a reservoir park in the model. We also add 2 kinds of tree crops and vineyards in the agriculture part. So this is basically the new version of the model looks like. This is a control center. It offers all links to the policy selection and the result summary. You can just click the button, go to the policy selection page, choose any policy you want to choose by changing the slider value. 0 means off, 1 means on. And when you're satisfied with the policy you choose, you just go to the policy selection summary page and click the accept and run button, run the simulation for this year, and forward to the next game year. And it also shows you all the policy you choose on this page. After that, you can just go to the result summary page. It shows you the agricultural yield in both graphs and tables. It also shows you the municipal water use, reservoir water level, storage. There are also fun pictures here to show, to represent the situation of the water use. Here you can see a beautiful lawn and a beautiful reservoir park. But if you're a bad player, it can also be like this. Yeah, it's bad, right? And here is a percent of the water demand being satisfied from the IDT Okanagan. Team red and team yellow, they all choose to ration the municipal water use. As I mentioned before, if you ration the municipal water use, the outdoor water use is first being suffered from it. So you can see this line is just going down, the green line. Since those 2 teams choose different times and amount of the water ration for the municipal water use purpose, these 2 lines are different, like this. And finally, they just get different picture of the lawn. Here, the purple line just decreased. The outdoor water use suffered from the ration for the municipal purpose. But for the red team, they also ration the outdoor water use, but they actually got a beautiful lawn. Look at this. And actually, their outdoor water use didn't suffer from it, but the indoor water use decreased. Do you know why? Because this team just to choose a policy. They choose to invest great water treatment to decrease their indoor water use and move the actual amount of water for the outdoor use purpose. Then they can just get a picture like this. Okay, this is a model application. The model can be used for the drought management, drought preparedness, and risk reduction. Also, long-term basin planning, how you allocate your limited supply to meet the basin demands. Policy analysis, water management policy, land management policy, and the model also includes some technological changes. Public and student drought education as well. Next step, we want to improve the new version of the model to better loading and comparing the different teams' policy, compare the different result of each turn for the policy sensitivity analysis purpose. We also wanted to validate this model. It's already in progress. And right now, the water supply part modeling is really simple. We wanted to translate the sacramental soil moisture accounting model, which developed in the Fortran language, to our system dynamic models, which is developed in the Wang software, and run this new model in a sub-annual time step. Right now, the model running at the annual time step. And once we move from the annual time step to the sub-annual, we can get more accurate agricultural yield. Also, in some of the months, it's very important of the stream flow for the fish spawning. So we wanted to try sub-annual time steps later.